Welcome to my week 6 demonstration. I'm going to be playing with food coloring and water. So we were asked to verify that the partial differential equation shown here as equation number 1 has a general solution of the form 2 for all possible values of q greater than 0. I took equation 2 and plugged it into Wolfram Alpha, found the partial with respect to x to be that is shown in equation 3, and the second partial with respect to x is shown in equation 4. And then I took the partial with respect to t in equation 5 and take a look at the right-hand side of equations 4 and 5, and they are awfully close except for the constant d in equation 5. And I recall now that equation 1 is supposed to have a d in it, so there's an error in my equation 1. It should actually be that the partial with respect to t is equal to d times the second partial with respect to x of the concentration function. I used a syringe filled with food coloring and took a transparent pie plate, set it on the kitchen table, the kitchen counter, and dropped in a drop and took sequential pictures and then added a few more drops and a few more drops. You can see they're all nicely expanding. Now for the analysis, first thing I did was take the leftmost dot and average out the width over a certain period of it. And you can see here that it's slowly getting wider and wider. And the little blips that you see in the data every once in a while are when I have brought the syringe in to add a drop to another location. Now if I plot the standard deviation of this curve, I see that I've got more or less a smooth curve where you can see the blips when I put in the syringe for the new one. Now we're asked to estimate d based on the plot that we just saw. And as we saw earlier, the concentration is a function of time, and x is given by equation 1. And we were told that the Gaussian distribution is proportional to the same equation. Now, if we look at just the denominator without the exponential, we can see by extension that 2 pi times the variance is equal to 4 pi times diffusion times time. So if we do the division, we can see that the diffusion constant is equal to 2 sigma squared over t. And if I plot an ideal 1 over x function, we see here that the form of that equation is pretty similar to what we saw in experimental results. I also took a look at what the averaging was across when I put the 3 drops in. Here you can see the first drop growing ever so slowly. There's the second drop. And finally, here's the third drop. And eventually, after leaving it in the pie plate for a long time, it was entirely filled. Now, I wanted to take a look at whether I could induce some accumulation. So I took some Easter egg dye and put it in and watched as it grew bigger and bigger. It's interesting to see that the yellow and the green dyes seem to diffuse at a different rate in this one. Unfortunately, I didn't clean the pie plate off on the bottom, so a lot of the noise that you see on here is because of water droplets. But after a while, it became interesting to see that at the edge, it appeared the diffusion was a linear straight line. So I repeated the experiment with some different food coloring tablets, and you can see that at the way beginning, the surface of the water appears to become diffused very quickly with a larger blob underneath the surface of the water. Now this food coloring appears to have some accelerant in it to try and make the Easter egg dyes diffuse into your water cup more quickly. So we see some time-dependent behavior. If I take the same data and plot the density using MATLAB, you can see here the wiggles, the oscillations there off in the tails where the dye is being spit out. And we also see the central area growing, what I assume to be underneath the water, growing slowly, slowly. And I start to see those straight lines on the end. And if we look the course notes from lecture 14, the diffusion equation with no accumulation shows a straight line when we have flux coming into one side of the container. So although I didn't get the accumulation that I was expecting when I used the colored food dyes, I did have a pretty solid demonstration of equilibrium flux. So that is my demonstration for week 6. Thank you very much for watching.